Alright, people. Oh my god, this is, what is it? 57, 76, that's 19 pages. Oh boy, love it. Okay, we are starting part 2 of Quantum. Oh, my stomach just growled like a motherfucker. Part 2. Boy Physics. Oh boy, physics. Let's get going. So we have 3 quotes here. Physics at the moment is again very muddled. In any case, for me it is too complicated, and I wish I were a film comedian or something of that sort. I had never heard anything about physics. And that's by Wolfgang Pauli. The more I think about the physical portion of the Schrödinger theory, the more repulsive I find it. What Schrödinger writes about the visualizability of his theory is probably not quite right. In other words, it's crap. And that's by Werner Heisenberg. The Heisenberg. If all this damned quantum jumping were really here to stay, I should be sorry I ever got involved with quantum theory. And that's by the Erwin Schrödinger himself. Alright, chapter 7. Spin Doctors. One wonders what to admire most: the psychological understanding for the development of ideas, the sureness of mathematical deduction, the profound physical insight, the capacity for lucid, systematic presentation, the knowledge of the literature, the complete treatment of the subject matter, or the sureness of critical appraisal. Einstein was certainly impressed by the mature, grandly conceived work he had just reviewed. It was difficult for him to believe that the 237-page article with 394 footnotes on relativity was the work of a 21-year-old physicist who had been a student and just 19 when asked to write it. Wolfgang Pauli, later nicknamed the Wrath of God, was acerbic and regarded as a genius comparable only with Einstein. Indeed, from the point of view of pure science, said Max Born, his one-time boss, he was possibly even greater than Einstein. And there's an early break. When's the next break? My god, there are no breaks until 12 pages in. Fuck. Okay. Wolfgang Pauli was born on 25th of April 1900 in Vienna, a city still in the grip of fin de siècle anxiety while enjoying the good times. His father, also called Wolfgang, had been a physician, but abandoned medicine for science, and in the process changed his family name from Pascheles to Pauli. The transformation was complete as he converted to Catholicism amid fears that the rising tide of anti-Semitism threatened his academic ambitions. His son grew up knowing nothing of the family's Jewish ancestry. At university, when another student said he must be Jewish, Wolfgang Jr. was astonished. I? No, nobody has ever told me that, and I don't believe that I am. He learned the truth from his parents during his next visit home. His father felt vindicated by the decision to assimilate when, in 1922, he was appointed to a coveted professorship and became the director of a new institute for medical chemistry at Vienna University. Pauli's mother, Berta, was a well-known Viennese journalist and writer. Her circle of friends and acquaintances meant that Wolfgang and his sister Herta, 6 years his junior, grew up accustomed to seeing leading figures from the arts as well as science and medicine at the family home. His mother, a pacifist and socialist, exerted a strong influence on Pauli. The longer the First World War dragged on through his formative teenage years, the keener became his opposition against it, and generally against the whole establishment, recalled a friend. When she died 2 weeks before her 49th birthday in November 1927, an obituary in the Neue Freie Presse described Bertha as one of the few truly strong personalities among Austrian women. Pauli was academically gifted, but far from a model pupil, finding school unchallenging. He began having private tuition in physics to compensate. Before long, when bored by a particularly tedious lesson at school, he began reading Einstein's papers on general relativity hidden under his desk. Physics had always loomed large in his young life in the form of the influential Austrian physicist and philosopher of science, Ernst Mach, his godfather. For one who would later enjoy the company and friendships of the likes of Einstein and Bohr, Pauli said that the constant contact with Mach, whom he last saw in the summer of 1914, was the most important event in my intellectual life. In September 1918, Pauli left what he called the spiritual desert that was Vienna. With the Austro-Hungarian Empire on the verge of extinction and Vienna's past glories faded, it was the lack of top-flight physicists at the city's university that he was lamenting. He could have gone almost anywhere, but went to Munich to study with Arnold Sommerfeld. Having recently turned down a professorship in Vienna, Sommerfeld had already been in charge of theoretical physics at Munich University for a dozen years when Pauli arrived. From the beginning, in 1906, Sommerfeld set out to create an institute that would be a nursery of theoretical physics. It was not as grand as the Institute Bohr would soon create in Copenhagen, consisting as it did of only 4 rooms: Sommerfeld's office, a lecture theater, a seminar room, and a small library. There was also a large laboratory in the basement where in 1912, Max von Lau's theory that X-rays were short wavelength electromagnetic waves was tested and confirmed, bringing quick recognition to the nursery. Sommerfeld was an exceptional teacher with the uncanny knack of setting his students problems that tested but did not exceed their abilities. Having already supervised more than his fair share of talented young physicists, Sommerfeld soon recognized Pauli as someone of rare and exceptional promise. He was a man not easily impressed, but in January 1919, a paper on general relativity written by Pauli before leaving Vienna had just been published. In his nursery, he had a first-year student, not yet 19 years old, who was already regarded by others as an expert in relativity. I don't want to read anymore. Already 19? Fucking hell. Pauli quickly became known and feared for his sharp and incisive criticism of new and speculative ideas. Some would later call him the conscience of physics for his uncompromising principles. Stout, with bulging eyes, he was every inch the Buddha of physics, albeit one with a biting tongue. Whenever he was lost deep in thought, Pauli unconsciously rocked back and forth. It was acknowledged far and wide that his intuitive grasp of physics was unmatched among his contemporaries and probably not even surpassed by Einstein. He judged his own work even more harshly than that of others. At times, Pauli understood physics and its problems too well, and that hampered the free exercise of his creative powers. Discoveries that he might have made if his imagination and intuition had roamed a little more freely went instead to colleagues less talented and unconstrained. The only person towards whom he was and remained diffident was Sommerfeld. Even as a celebrated physicist, whenever Pauli found himself in the presence of his former professor, those who had been on the receiving end of his sharp judgments were always amazed to see the wrath of God, responding with "Ja, Herr Professor," "Nein, Herr Professor." They hardly recognized the man who had once ticked off a colleague. "I do not mind if you think slowly, but I do object when you publish more quickly than you think." Or on another occasion, saying of a paper he had just read, "It is not even wrong." He spared no one. "You know, what Mr. Einstein said is not so stupid," he told a packed lecture theater while still a student. Sommerfeld, sitting in the front row, would not have tolerated such a remark coming from any of his other students, but then he knew none of them would have uttered it. When it came to evaluating physics, Pauli was self-confident and uninhibited even in the presence of Einstein. In a clear sign of the high regard in which he held Pauli, Sommerfeld asked him to help write a major article on relativity for the Encyclopädie der Mathematischen Wissenschaften. Paul Sommerfeld had accepted the task of editing the 5th volume of the Encyclopädie that dealt with physics. After Einstein declined, Sommerfeld decided to write on relativity himself, but found he had little time to do so. He needed help and turned to Pauli. When Sommerfeld saw the first draft, it proved to be so masterly that I renounced all collaboration. It was not only a brilliant exposition of the special and general theories of relativity, but an unrivaled review of the existing literature. It remained for decades the definitive work in the field and drew Einstein's wholehearted praise. The article appeared in 1921, 2 months after Pauli received his doctorate. As a student, Pauli preferred to spend his evenings enjoying the Munich nightlife in some cafe or other, returning to his lodgings to work through much of the night. He rarely attended lectures the following morning, turning up only around noon, but he attended enough to be drawn to the mysteries of quantum physics by Sommerfeld. I was not spared the shock which every physicist accustomed to the classical way of thinking experienced when he came to know Bohr's basic postulate of quantum theory for the first time, Pauli said more than 30 years later, but he quickly got over it as he set about tackling his doctoral thesis. Sommerfeld has set Pauli the tasks of applying the quantum rules of Bohr and his own modifications to the ionized hydrogen molecule, in which one of the 2 hydrogen atoms that make up the molecule has had its electron ripped off. As expected, Pauli produced a theoretically impeccable analysis. The only problem was that his results did not agree with the experimental data. Used to one success after another, Paul was despondent at this lack of agreement between theory and experiment. However, his thesis was regarded as the first strong evidence that the outer limits of the Bohr-Sommerfeld quantum atom had been reached. The ad hoc way in which quantum physics was bolted onto classical physics had always been unsatisfactory, and now Pauli had shown that the Bohr-Sommerfeld model could not even deal with the ionized hydrogen molecule, let alone more complex atoms. In October 1921, armed with his doctorate, Pauli left Munich for Göttingen to take up the post of assistant to the professor of theoretical physics. Max Born, 38, a key figure in the future development of quantum physics, had arrived in a small university town from Frankfurt just 6 months before Pauli. Growing up in Breslau, capital of the then Prussian province of Silesia, I'm reading. Growing up in Breslau, capital of the then Prussian province of Silesia, it was mathematics, not physics, that attracted Born. His father's, like Pauli's, was a highly cultured medical man and academic. A professor of embryology, Gustav Born advised his son not to specialize too early once he enrolled at Breslau University. Dutifully, Born settled on astronomy and mathematics only after having attended courses in physics, chemistry, zoology, philosophy, and logic. His studies, including time at the universities of Heidelberg and Zurich, ended in 1906 with a doctorate in mathematics from Göttingen. Immediately afterwards, he began a year of compulsory military service that was cut short because of asthma. After spending 6 months in Cambridge as an advanced student, where attending the lectures of J.J. Thomson, Bohr returned to Breslau to begin experimental work, but quickly discovering that he possessed neither the patience nor the skills required to be even a competent experimenter, Bohr turned to theoretical physics. By 1912, he had done enough to become a Privatdozent in the world-renowned mathematics department at Göttingen, where they believed that physics is much too hard for physicists. Born's success in tackling a string of problems by harnessing the power of mathematical techniques unknown to most physics led in 1914 to an extraordinary professorship in Berlin. Just before war broke out, another newcomer arrived at the epicenter of German science, Einstein. Before long, the two men, who shared a passion for music, became firm friends. When war came, Born was called up for military service. After a spell as a radio operator with the Air Force, he spent the rest of the war conducting artillery research for the Army. Fortunately stationed near Berlin, Bohr was able to attend seminars at the university, meetings at the German Physical Society, and musical evenings at Einstein's home. After the war, in the spring of 1919, Max von Laue, an ordinary professor at Frankfurt, suggested to Born that they swap posts. Laue had won the 1914 Nobel Prize for the theory beyond the diffraction of X-rays by crystals, and wanted to work with Planck, his former supervisor and the scientist he idolized. Born, encouraged by Einstein to definitely accept, agreed, and the exchange meant promotion to a full professorship and independence. Less than 2 years later, he moved to Göttingen to head the university's Institute of Theoretical Physics. It consisted of one small room, one assistant, and a part-time secretary, but Bohr was determined to build on these humble beginnings and institute to rival Sommerfeld's in Munich. High on his list of priorities was getting Wolfgang Pauli, whom he described as the greatest talent in the physics area that had emerged in the last years. Born had already tried once before and failed, as Pauli opted to stay in Munich to finish his doctorate. This time, he got his man. Wolfgang Pauli is now my assistant. He is amazingly excellent and very able, Born wrote to Einstein. Soon he discovered that the hired help had his own way of doing things. Pauli might have been brilliant, but he put in long hours of hard thinking as he continued his practice of working into the middle of the night and sleeping late. Whenever Born was unable to give his 11 o'clock lecture, the only way he could ensure Pauli would be there to teach in his place was by sending the maid to wake him up at 10:30 a.m. It was clear from the beginning that Pauli was an assistant in name only. Bohr admitted later that he learned more from Pauli, despite his bohemian ways and poor timekeeping, than he was able to teach the infant prodigy. He was sad to see him go in April 1922. He was sad to see him go when in April 1922, Pauli left to become an assistant at Hamburg University. Swapping the quiet life of the small university town that he could hardly bear for the bustling nightlife of the big city was not the only reason he left so quickly. Pauli trusted his sense of physical intuition in pursuit of a logically flawless argument when tackling any physics problem. Born, however, turned much more readily to mathematics and allowed it to lead his search for a solution. 2 months later, in June 1922, Pauli was back in Göttingen to hear Bohr's celebrated lecture series and met the Great Dane for the first time. Impressed, Bohr asked Pauli if he would come to Copenhagen for a year as his assistant to help edit work in progress for publication in German. Pauli was taken aback by the offer. I answered with that certainty of which only a young man is capable. I hardly think the scientific demands which you will make on me will cause any difficulty, but the learning of a foreign tongue like Danish far exceeds my abilities. I went to Copenhagen in the fall of 1922, where both my contentions were shown to be wrong. It was also, he recognized later, the beginning of a new phase in his life. Aside from helping Bohr, Pauli made a serious effort in Copenhagen to explain the anomalous Zeeman effect, a feature of atomic spectra that the Bohr-Sommerfeld model could not explain. If atoms were exposed to a strong magnetic field, then the resulting atomic spectra contained lines that were split. It was quickly shown by Lorentz that classical physics predicted a splitting of a line into a doublet or a triplet, a phenomenon known as the normal Zeeman effect, which Bohr's atom could not accommodate. Fortunately, Sommerfeld came to the rescue with two new quantum numbers, and the modified quantum atom resolved the problem. It involved a series of new rules governing electrons jumping from one orbit or energy level to another based on three quantum numbers, n, k, and m, that describe the size of the orbit, the shape of the orbit, and the direction in which the orbit was pointing. But the celebrations were short-lived when it was discovered that the splitting of the red alpha line in the spectrum of hydrogen was smaller than expected. This situation grew worse with the confirmation that some special lines actually split up into a quartet or more instead of just two or three. Although called the anomalous Zeeman effect because the extra lines could not be explained using either existing quantum physics or classical theory, it was in fact far more common than the normal effect. For Pauli, it signified nothing less than the deep-seated failure of the theoretical principles known till now. Having set himself the task of rectifying this miserable state of affairs, Pauli could not come up with an explanation. Up till now, I've thoroughly gone wrong, he wrote to Sommerfeld in June 1923. Consumed by the problem, Pauli later admitted that he was in complete despair for some time. One day, another physicist from the institute met him while strolling around the streets of Copenhagen. "You look very unhappy," said his colleague. Pauli turned on him. "How can one look happy when he is thinking about the anomalous Zeeman effect? The use of ad hoc rules to describe the complex structure of atomic spectra was just too much for Pauli. He wanted a deeper, more fundamental explanation of the phenomenon. Part of the problem, he believed, was the guesswork involved in Bohr's theory of the periodic table. Did it really describe the correct arrangement of electrons inside atoms? By 1922, the electrons in the Bohr-Sommerfeld model were believed to move in three-dimensional shells. These were not physical shells, but energy levels within atoms around which electrons seemed to cluster. A vital clue in helping Bohr construct this new electron shell model was the stability of the so-called noble gases: helium, neon, argon, krypton, xenon, and radon. With atomic numbers of 2, 8, 10, 18, 36, 54, and 86, Okay, give me 5 minutes. The relatively high energies required to ionize any noble gas atom, that is, to rip away an electron and turn it into a positive ion, together with their reluctance to chemically bond with other atoms to form compounds, suggested that the electron configurations in these atoms were extremely stable and consisted of closed shells. The chemical properties of the noble gases were in stark contrast to the elements that preceded them in the periodic table: hydrogen and the halogens, fluorine, chlorine, bromine, iodine, and astatine. With atomic numbers 1, 9, 17, 35, 53, and 85, all these elements easily form compounds. Unlike the chemically inert noble gases, hydrogen and the halogens united with other atoms because, in the process, they picked up another electron and thereby filled the single vacancy in the outermost electron shell. By doing so, the resultant negative ion had a completely full or closed set of electron shells and acquired the highly stable electronic configuration of a noble gas atom. Mirroring the halogens, the alkali group, that is lithium, sodium, potassium, rubidium, cesium, and francium, were quick to lose an electron as they formed compounds and became positive ions with the electron distribution of a noble gas. The chemical properties of these three groups of elements form part of the evidence that led Bohr to propose that the atom of each element in a row of the periodic table is built up from the previous element by the addition of another electron to the outer electron shell. Each row would end with a noble gas in which the outer shell was full. Since only electrons outside the closed shells, called valence electrons, took part in chemical reactions, atoms with the same number of valence electrons shared similar chemical properties and occupied the same column in the periodic table. The halogens also all had 7 electrons in the outermost shell, requiring just one more electron to close it and acquire an electron configuration of a noble gas. The alkalis, on the other hand, all have 1 valence electron. It was these ideas that Pauli heard Bohr outline during the Göttingen lectures in June 1922. Sommerfeld had greeted the shell model as the greatest advance in atomic structure since 1913. If he could mathematically reconstruct the numbers 2, 8, 18 of the elements in the rows of the periodic table, then it would be, Sommerfeld told Bohr, the fulfillment of the boldest hopes of physics. In truth, there was no hard mathematical reasoning to back up the new electron shell model. Even Rutherford told Bohr that he was struggling to form an idea of how you would arrive at your conclusions. Nevertheless, Bohr's ideas had to be taken seriously, especially after the announcement in his Nobel lecture in December 1922 that the unknown element with atomic number 72, later called hafnium, did not belong to the rare earth group of elements, was later confirmed to be correct. However, there is no organizing principle or criteria behind Bohr's shell model. It was an ingenious improvisation based on an array of chemical and physical data that could, in large part, explain the chemical properties of the various groupings of elements in the periodic table. In crowning glory was hafnium. As he continued to fret over the anomalous Zeeman effect and the shortcomings of the electron shell model, Pauli's time in Copenhagen came to an end. In September 1923, he returned to Hamburg, where the following year he was promoted from assistant to Privatdozent. But with Copenhagen a short train journey and a ferry across the Baltic Sea, Pauli was still a regular visitor to the Institute. He concluded that Bohr's model could only work if there was a restriction on how many electrons could occupy any given shell. Otherwise, in contradiction of the results of atomic spectra, there seemed nothing to prevent all the electrons in any atom from occupying the same stationary state or the same energy level. At the end of 1924, Pauli discovered the fundamental organizing rule, the exclusion principle, that provided a theoretical justification that had been missing in Bohr's empirically devised electron shell atomic model. Pauli was inspired by the work of a Cambridge postgraduate student, Edmund Stoner, or 35, who was still working on his doctorate under Rutherford. When in October 1924, his paper, The Distribution of Electrons Among Atomic Levels, was published in the Philosophical Magazine. Stoner argued that the outermost or valence electron of an alkali atom has as many energy states to choose from as there are electrons in the last closed shell of the first inert noble gas that follows it in the periodic table. For example, lithium's valence electron could occupy any one of 8 possible energy states, exactly the number of electrons in the corresponding closed shell of the gas neon. Stoner's idea implied that a given principal quantum number n corresponds to a Bohr electron shell which would be completely full or closed when the number of electrons it contains reaches twice its number of possible energy states. If each electron in an atom is assigned the quantum numbers n, k, m, and each unique set of numbers labels a distinct electron orbit or energy level, then according to Stoner, the number of possible energy states for, say, n equals 1, 2, and 3 would be 2, 8, and 18. For the first shell, n equals 1, k equals 1, and m equals 0. For the first shell, n equals 1, k equals 1, and m equals 0. These are the only possible values that the 3 quantum numbers can have, and they label the energy state 110. But according to Stoner, the first shell is closed when it contains 2 electrons, double the number of available energy states. For n equals 2, either k equals 1 and m equals 0, or k equals 2 and m equals 0, negative 1, or 1. Thus, in the second shell, there are 4 possible sets of quantum numbers that can be assigned to the valence electron and the energy states it can occupy: 210, 22-1, 220, or 221. Therefore, the shell n equals 2 can accommodate 8 electrons when it's full. The third shell, n equals 3, has 9 possible electron energy states: 310, 32-1, 320, 321, 33-2, 33-1, 330, 331, 332. Using Stoners' rule, the n equals 3 shell can contain a maximum of 18 electrons. Pauli had seen the October issue of the Philosophical Magazine, but ignored Stoners' paper. Not known for his athleticism, Pauli ran to the library to read it after Sommerfeld mentioned Stoners' work in the preface to the 4th edition of his textbook, Atomic Structure and Spectral Lines. Pauli realized that for a given value of n, the number of available energy states n in an atom that an electron could occupy was equivalent to all the possible values that the quantum numbers can n could take, and was equal to 2n squared. Stoners' rule yielded the correct series of numbers 2, 8, 18, 32 for the elements in the rows of the periodic table. But why was the number of electrons in a closed shell twice the value of n, or n squared? Wait. Oh, the number of... Let me read this paragraph again. Pauli had seen the October issue of the Philosophical Magazine, but ignored Stoners' paper. Not known for his athleticism, Pauli ran to the library to read it after Sommerfeld mentioned Stoners' work in the preface to the 4th edition of his textbook, Atomic Structure and Spectral Lines. Pauli realized that for a given value of n, the number of available energy states, capital N, in an atom that an electron could occupy was equivalent to all the possible values that the possible values that the quantum numbers k and m could take, and this was equal to 2n squared. Stoners' rule yielded the correct series of numbers 2, 8, 18, 32, ... for all the elements in the rows of the periodic table. But why was the number of electrons in a closed shell twice the value of capital N, or n squared? Pauli came up with the answer. A fourth quantum number had to be assigned to electrons in atoms. Unlike the other numbers n, k, and m, Pauli's new number could have only two values, so he called it Zweideutigkeit. It was this two-valuedness that doubled the value of electron states. Where there had previously been a single energy state with a unique set of three quantum numbers, n, k, and m, there were now two energy states, nkma and nkmb. These extra states explained the enigmatic splitting of spectral lines of the anomalous Zeeman effect. Then the two-valued fourth quantum number led Pauli to the exclusion principle, one of the great commandments of nature. No two electrons in an atom can have the same set of four quantum numbers. The chemical properties of an element are not determined by the total number of electrons in its atom, but only by the distribution of its valence electrons. If all the electrons in an atom occupied the lowest energy level, then all the elements would have the same chemistry. It was Pauli's exclusion principle that managed the occupancy of the electron shells in Bohr's new atomic model and prevented them all from gathering in the lowest energy level. The exclusion principle provided the underlying explanation for the arrangement of the elements in the periodic table and the closing of shells with chemically inert rare gases. Yet despite these successes, Pauli admitted in his paper on the connection between the closing of electron groups in atoms and the complex structure of spectra, published in 21st of March 1985 in Zeitschrift für Physik, we cannot give a more precise reason for this rule. Yes, I know. Why 4 quantum numbers and not 3 were needed to specify the position of electrons in an atom was a mystery. It had been accepted since the seminal work of Bohr and Sommerfeld that an atomic electron in orbital motion around a nucleus moves in 3 dimensions and therefore requires 3 quantum numbers for its description. What was the physical basis of Pauli's 4th quantum number? In the late summer of 1925, 2 Dutch postgraduate students, Samuel Goldschmidt and George Uhlenbeck, realized that the property of two-valuedness that Pauli had proposed was not just another quantum number. Unlike the 3 existing quantum numbers n, k, and m that specified the angular momentum of the electron in its orbit, the shape of its orbit, and its spatial orientation respectively, two-valuedness was an intrinsic property of an electron that Goldschmidt and Uhlenbeck called spin. It was an unfortunate choice of name that conjured up images of spinning object, but electron spin was a purely quantum concept that solved some of the problems still besetting the theory of atomic structure while neatly providing the physical justification of the exclusion principle. And fucking finally, that's a break. And I have to eat noodles, so sorry.